In this lab, we are making cyclohexythreene carboxylic acid methyl ester. This is a Diels Alder reaction. So let's first draw this structure. Okay, so this is the structure that we are making. Okay, we know that with Diels Alder reaction, our product is going to be a cyclohexene. So since we were given the product, what we can do is we need to find from this product our diene and our dienophile. Okay, so you go to the cyclohexene, and then what we need to do is we need to number the cyclohexene every single time. So you start numbering from the top, give the double bond numbers 2 and 3. This is 4, this is 5, and this is 6. So we know that 5, 6 comes from the dienophile. Okay, and then the 1, 2, 3, 4, this is the diene. So the bonds that we would need to break in here are the bonds between 1 and 6, because these are the bonds that you're forming, and the bond between 4 and 5. So you break those, and then you can easily determine now your diene. This is what we need to choose. So the diene over here is the 1,3-butadiene. 1,3, yeah, it is the 1,3-butadiene. So you're choosing here the 1,3-butadiene. This is going to be your diene. And then your dienophile, in this case, you're going to put a double bond between carbons 5 and 6. And then the rest of the substituent on carbon number 5. So this is the diene and the dienophile that we would need to choose in order to make this cyclohexene product. Okay, so we're going to go to the experiment. Make sure that your experiment opens to the Diels-Alder reaction. From here, you're going to choose your chemicals. So we said that we would need the 1,3-butadiene. Guys, every time you hit on a chemical, it's just going to disappear. So you cannot use it again. If you want to use it again, you have to close the experiment and start all over again. So now in my flask, I do have the 1,3-butadiene. So this is going to be my diene. And then my dienophile, I need the methyl acrylate. Okay, so let me double check in here. So this is going to be the methyl acrylate that is going to act as a dienophile. So we would need to have that as well. These are the two reactants that we need for the Diels-Alder reaction. The reaction will not happen without a solvent. So you would need to pick a solvent from these. We know that these are hydrocarbons, not water soluble, so we would need to use the diethyl ether. If you bring your cursor to the flask, you should see all the three chemicals on the bulletin board. So we're going to bring this all the way here. Now we have everything ready, okay? We know Diels-Alder reaction happens in presence of heat. So we would need the heating mannitol. Definitely the reaction will not happen if we do not put a condenser. So make sure that you have your condenser, make sure that you have your nitrogen gas in there. I don't need anything else from here. I have everything I need in my flask. Don't start the experiment yet, or don't start the reaction yet. We would need to get a TLC before that. Okay. So go ahead and get the RF value for the TLC. And again, RF value has a maximum value of 1. It cannot be greater than 1. And 1 means that it is all the way to the solvent front. So pay attention over here. So this is going to be your RF value. You're going to measure from the midpoint of the center to the spotting line. So this is going to be your distance here, and you're going to divide it by the full distance up there. Okay, your value should be less than 1. This is going to be your starting RF value. We're going to save the TLC. This is going to be before the reaction is going to automatically save in the lab book. So this is going to be your lab book. If you go to your lab book, you should see your TLC in there. We're going to go back to the live data. So in the live data, what do we have? We have our reactants and we have our solvent in there. We do have our TLC. Everything is ready. We're going to start this experiment. This experiment is going to take an hour or so in order to get done. So we're going to go ahead and process this with an hour. First, let me start. Okay. So we're going to do 1 hour. So see, after 1 hour, I still have the remaining reactants, and I formed some of the product. So most of our reactants turned into product, but not all of them. So I cannot stop the reaction. I need to proceed further. This is the 2nd hour. I still have reactants remaining. And this is the 3rd hour. Now, 3 hours are more than enough. I got my product in there. Make sure this is going to be the same product as you're asked to synthesize over here. Okay, so after you get your product, we're going to go ahead and no, before TLC, we're going to go ahead and do the extraction, you guys, because we want to get rid of the diethyl ether. And this is organic, right? And your product is dissolved in an organic solvent. So we would need to separate the product. So we don't have an acid, we don't have a base, so we're not going to use neither NaOH or HCl. We're going to keep it simple, and we're just going to add water, just creating an organic and aqueous layer in there. And I know that my product is in the organic, so I'm just going to pick the organic. And here you go, this is going to be my product. The ether will directly evaporate, so I will be left only with my product. So once you're left with your product in there, now we're going to go ahead and take the TLC for that. And you're going to calculate the RF value in there. Please make sure again, RF value should be less than 1. It cannot be more than 1. And here it seems like it is in the middle, so it's like around 0.5. In this case. So let's go ahead and hit save. This is going to be for the final product. Now you're going to get the IR, and we're going to get the proton NMR. So we said, like with the IR, we're going to read from left to right. Okay, from left to right. Let me put the structure in front of me over here. It will be easier. Okay, so here you go. So let's go ahead and see what do we have. So for the FTIR, let me make this smaller, make this a little bit bigger so that I can write it. So from left to right, I know that I do have my ester functional group, right? So I'm going to have my ester functional group, and I'm going to have my alkene functional group. So these are the functional groups that I would need to focus on. So I'm going to start with the rest are simply alkanes. We're going to ignore this one over here because it is the sp3ch stretches that I have on 4 and on 6 and on also 1. These are sp3ch stretches and on 5 as well. So I'm just going to ignore those and start here with the carbonyl. This is the C double bond O. This is position 1 in there, which is around 1750 over here. So that the C double bond O over here is around 1750 centimeter to the -1. This is going to be position number 1, and it is for the C double bond O, okay, of the ester. And now the second position. Esters have two positions that are very important, two vibrations that are very important in the FTIR. One is at 1750 and the other one is at 1200. So see that the 1200 in there? This is the CO of the ester. So what CO of the ester? It's the sp2. So the sp2CO. Let's highlight that. So the sp2CO of the ester here, this appears at 1200 centimeter to the -1. This is position number 2. So these are the two functional groups or the two vibrations for the ester functional group. Okay, there's another one because over here I do have an sp3CO stretch. So this is going to be different now. So let's use another color. So here it's going to be an sp3CO stretch in there. So the sp3CO stretch, it's going to show at 1025 centimeter to the -1. And this is again the CO of the ester, but it is the sp3CO stretch. This is position 3, and it should show at 1025 centimeter to the -1. Guys, this is the IR table that I posted. So use that because you do have the sp2co stretch, the sp3co stretch, and this is from where I'm getting my numbers in there. Okay, so that is going to be my position number 3. Now, position number 4 and 5, because they asked you to label 5 functional group in there. It's going to be for the alkene, you guys, because I do have my C double bond C of the alkene. So this is going to be the C double bond C of the alkene. And the C double bond C of the alkene has 2 vibrations. One is around probably 900 centimeter to the -1. You're going to see a peak. So this one over here, this is the C double bond C of the alkene. And this one also is the C double bond C of the alkene. It's around 700, okay? Around 690. Yeah, 690 centimeter to the -1. So these two are my positions 4 and 5, and around 700 centimeter to the -1. And this is the vibrations of the alkene. Okay, so that is for the FTIR. You're going to save that, and after we save it, let's go ahead and close it. And after we close, let's do the proton NMR. Oh, by the way, when I do the proton NMR, just make sure that it is hydrogen NMR and not carbon-13, okay? Because it can switch. If you just tap on it, it's going to switch to carbon-13. So pay attention because carbon-13 has a bigger scale. It's from 0 to 200 parts per million versus the proton NMR, which is from 0 to kind of like 10 parts per million. Here it shows 10, but the actual scale is at 12 parts per million. Okay, so let's go ahead and make this a little bit smaller. Every time you do have an alkene with proton NMR, the proton NMR spectrum, it's going to be a little bit more complicated because of all the vibrations around the C double bond, C. So let's go ahead and draw that. There you go. So that is going to be our ester. So what do we have in here? Let's draw the different types of hydrogens that we have. So basically we have the hydrogens around the alkene. And the hydrogens around the alkene, if you look at the proton NMR table, let's see. So for the proton NMR table, here you go. This is carbon-13. This is carbon-13. Here you go. This is the proton NMR table. So around the alkene. So the C double bond C, these are the most de-shielded in there. It's between 4.5 and 6.5. So I'm assuming these two guys, position 1 and position 2, these are for the hydrogens around the alkene. Okay. So these hydrogens in there are around the alkene. Now the one that is closest to the carbonyl is the one also which is the most de-shielded. So I'm expecting that this hydrogen, because it's closest to the carbonyl, that is going to be around, if I read this, it's around 5, you have 569 and 591, okay? Or 591. So I do have here, it's around 5.91 parts per million. And the other one, we said it is around 578 parts per million. These two are the hydrogens for the alkene, and each one of them has one hydrogen, okay? So each one of them has one hydrogen. Now for the splitting of this one, this hydrogen will be split by this hydrogen over here. You can see it's split into a doublet, and this one is split by the other one into another doublet. Okay. Let's see if we go ahead and we zoom in there. It seems like a doublet, and it seems like another doublet in there. Okay, and then what do we have? We have the singlet. Do you see the singlet? This is position number 3. We have a singlet in there. So that singlet, the only singlet that I see over here is for this CH3. So this one is a CH3. So let's write it down. This one is a CH3 in there. So C, it has 3 hydrogens. And it does make sense because see the 1 hydrogen integration versus the integration for the 3 hydrogens in there. This one is the most de-shielded, and it is around the 3 point, let's say 69 parts per million. So this is 3.69 parts per million. Now, how did I know that this one is the CH3? Because this one is the only singlet. So because this hydrogen is connected to no hydrogens in there, so it is the only singlet. And if you look at the proton NMR table, we look at this one because it's the CH3 connected to an O connected to the C double bond O. So if this R is a CH3, it's going to be around the 3.7 parts per million. And we do have that. So this one is around 3.7 parts per million. That's why we know that this is a CH3. This is going to be position number 3. Now for position number 4, we do have it at around 3.07. And this one is 1 hydrogen. Now, we are in the 3th region, right? And we know that this one is more de-shielded than the others because it is further downfield. So I'm expecting that position number 4 is actually 1 hydrogen. If you see it over here, this one is going to be 1 hydrogen. So position number 4 in there is going to be definitely next to the carbonyl. This is going to be our 1 hydrogen. So this one is around the 3 point, how much did we say? 3.08 parts per million in there. And this one appears to be actually it's hard to know how much, so I would look at it and I would say, okay, this hydrogen here is connected to 1, 2, 3, 4 hydrogens. Do you see? These are 4 hydrogens plus 1 is 5, so it's going to be a multiplet in there. It's hard to see that it is a multiplet, but definitely see it is a multiplet in there. So I would go ahead and just put it as a multiplet for this one. So this one is going to be position number 4 in there, and it does have 1 hydrogen 4. So position number 5 now, number 5 is going to be closer to it's going to be between the double bond and the carbonyl, so probably it's this one. This one's going to be position number 5 in there. It's because it's going to be the more de-shielded, okay, than position number 6, 7, and 8. And this one over here is this one has 2 hydrogens, and it's going to be around 2.57 parts per million. Okay, so again, we are looking at the positions and theirs. These are not the number of hydrogens, these are the positions of the peak. So please follow the position of the peak. So this is position number 5, 2.57. It does have 2 hydrogens, you guys, for position number 5. And then we do have position number 6 in there. So see, 6 and 7, they are kind of like connected with each other. So we do have position number 6, which is going to be, let's see over here. These are the only 2 that are left. So, and we do have position 6, 7, and 8. So we do have hydrogens here that are in different environments. So we have these 2 hydrogens here, and then we have these 2 hydrogens in there. Okay. These 2 hydrogens, for some reason, they are showing as 2 separate peaks. Now, in reality, they are just one. They should be just one peak in there, but they are showing as 2 separate peaks. Let's do these. These ones are closer to the C double bond O. So these ones are going to be around 1.86. So this is going to be position number 6 in there. And this is going to be around 1.86 parts per million. 1.86 has 2 hydrogens. And this 2 hydrogen is going to be split by its neighbors. How much neighbors? You do have 2 hydrogens here. You do have 1 hydrogen there plus 1. So it needs to be a quartet. Okay? So this one over here, which is position number 6, it's going to be a quartet. And then you do have position 7 and 8 over here. Again, those two, 7 and 8, they should appear to be one peak. They should not be, or one signal, I mean, not one peak, one signal. But here they are showing to be two different signals. This means that these two hydrogens are going to be different and they're going to split each other. So this hydrogen will be split by these two into a quartet, and this hydrogen is going to be split by those two into a quartet as well. We're going to choose the one that is closest to the simply to the double bond or to the carbonyl to be further downfield. So this hydrogen over here, it's going to be the allylic hydrogen. And if you look at the NMR table, this is the allylic hydrogen. It tells you that the allylic hydrogen is between 1.5 and 2.6. So it's basically in this region in there. So this is the allylic hydrogen there. So this one is going to be around 1.80 parts per million. And this one over here is going to be around 1.48 parts per million. Okay. So this is going to be the splitting pattern for this structure. Please, you guys, follow the same order. We read our proton NMR from left to right. Do not start it from right to left. You're going to mess everything up. And when you are calculating the splitting pattern, always look at the hydrogen that you are working with. Look at the neighboring hydrogens, add them up, and add +1. So for this one over here, for this hydrogen, it's connected to 1, 2, 3, 4. So 4 hydrogens +1, so it's going to be 5. More than 4, make it a multiplet. Okay? So more than 4, if there is no option for quintet, then make it a multiplet.